Hello, everybody. I hope you can hear me.
Perfect audio.
Perfect. Nice. Okay. Good. Then I think if everybody else is ready to start, I am ready to start. So welcome everybody to today's presentations. My name is Philipp Endres. I'm from the customer support team, and I'm going to present you some information about our current product, the Electrolyser EL 4.0. We're gonna do a deep dive. So gonna check out everything which is related to the device. And of course, you always have the possibility to ask questions. So feel free to just write in the chat and let us know. All right. So let's start. Okay. First of all, let's talk about how the EL 4.0 was created. So we have our development mindset of stopping fossil fuels. This is our main goal. We want to use renewable energies to create green hydrogen. And our goal is to make hydrogen much cheaper than it is today. And we are taking the way of standardization and mass production to reach this goal, because we are convinced that only if we have small modular devices which are easy to set up and easy to scale up, then we are able to make the hydrogen price drop and be a real competitor to fossil fuels. Therefore, we are following our main principles of urgency, simplicity, and transparency, which are also deeply integrated into our products. So we are continuously working on improving our machines, and we want to provide you a very simple and very easy to understand setup. And of course, we're also very transparent with our documentation and with our support. Okay, then let's take a look what happened in the past. So we started with the EL 500 in February 2018. And as you can see here on the left side, it is a comparably big device. It was also separated stack and control modules. And the further you go to the right, you can see the electrolyzers that we developed. They become smaller and smaller. They become lighter. They become more cost efficient. And of course, that's a big advantage. And now we reached 2022, and we finally created the EL Model 4, so the EL 4.0. And we again decreased the size, so now it's 6 units tall. Therefore, we have another 4.5 centimeters less in height. Also, we have a longer lifetime. We have 40% less weight. And we have still all the advantages from the previous models. We're also having more different types, but I will talk about that in a second. And so you see the sizes and the weights are going down, and of course we'll continue working on that. So we hope that with our next model we will even be further decreasing size and weight. Of course, with the same efficiency, with the same performance. Let's check out how the EL 4.0 has been designed. So for us, it was very important to have a modular approach. In general, that makes it faster to assembly. We have an easier and quicker maintenance. Of course, this is also a cost reduction argument. And not really related to the modular approach, but also complying with the ISO standards is also something that we considered during our development of the EL 4.0. So let's check out what's happening actually inside. So as you might know, the stack is the key component where all the magic is happening. And here I brought you a slide where you can see how hydrogen is actually created. So the water is passing through the gas and liquid diffusion layer, and then it enters through the membrane. Then hydrogen is created at the cathode and released via the gas diffusion layer. The OH minus is then recombining with other OH minus to water and oxygen, and water and oxygen is then transported back to the internal tank. So this is the AAM principle that we're using, and yeah, as you might know, compared to other systems, we have a very cost-efficient and a very environmental friendly approach. We don't need any rare materials like titanium and platinum, and yeah, so we still have the advantages of the alkaline and the PEM electrolyzers, but without their disadvantages, and that's what makes the AM stacks so special. We're using our AM stacks in both models. So we have the electrolyzer EL 4.0, and we are also working on the multi-core. I think you already heard about that as well. We will have another session tomorrow where we will hear even more about the multi-core. So I don't want to talk too much about it. But yeah, our approach of using the stack in both products make it actually, yeah, even more cost efficient and of course scalable. So as I said, when you have the AM stack in the electrolyzer, you're also able to scale those, and you can combine several electrolyzers EL 4.0 in a cabinet. And if you need even more hydrogen, you can just take several cabinets together and create even bigger kilowatt systems. Or if you really need a lot of hydrogen, you are also able to put several multi-cores together. So depending on your use case, you are flexible, and you can also scale up your hydrogen production side. If you want to start small and become big, that's not a problem at all. You can just extend your current setup very easily. And to do that, we're also working with integration partners. So if you cannot or don't want to do it by yourself, it's no problem. We are having a huge network of training partners with a huge network of integration partners who help you to set up your hydrogen systems. Okay, so I already talked about it. The EL 4.0 is available in four different types. So we have, so to say, the standard model EL 4.0. We just call it 4.0, and it's an air-cooled version with AC power supply. But we also have variations of that. So there's also a liquid-cooled unit, so you can attach it to your cooling circle if you have one. This becomes more useful with containerized solutions. We will also talk about that a little bit later. And the AC power supply can also be changed to a DC power supply. So depending on your individual setup, you have the choice between those four types. Okay, let's talk a little bit about the differences to our previous model, the EL 2.1. And I hope the slide is big enough so that you can read a little bit. What I brought you here are the two data sheets of the EL 2.1 and the EL 4.0. And what you can see is that all specifications, they basically remained the same, but the dimensions of the device and the weight became smaller. So we have less weight, we have less height, and therefore, the unit becomes even more flexible, easier to set up, and also easier to carry. So now I want to go a little bit more into detail what's happening inside the electrolyzer. So we already talked a little bit about the AM stack, but what's going on inside, like step by step? So I would like to start on the left side of the picture. So here you can see the electrolyte tank, which is filled up with electrolyte via the fill drain port. And of course, when water is used up, it has to be refilled. So this happens via an H2O in port in the top of the device. And then when the electrolyte is inside the tank, it is pumped through the heat exchanger and to the AM stack. So we have a kind of circular pumping here. So electrolyte is circulating here. And of course, I already talked about it. So the electrolysis happens in the AM stack. So here is where hydrogen is produced. It is then released via the H2 out. And we also have a component which extracts some water. So this water is then in form of a water vapor is then released via the H2 vent port. And on the other hand, we have the oxygen, which is going back to the tank, then here separating from the electrolyte, and then the oxygen is escaping via the O2 vent port. So this is basically what's happening here. And if you have the liquid cooled version, then you have additional ports in the, well, it's actually in the top of the device, but here we draw it in the bottom to make it a little bit easier. So the two ports are a cooling in and a cooling out. So you will just attach your cooling circle here, and it will cool the electrolyte and keep the electrolyte and therefore also the stack at a steady temperature of 55 degrees. We found out that this is the perfect temperature to produce hydrogen efficiently, and that's why it is keeping the temperature around 55. So 53 to 56 maybe. Okay, so now you're probably wondering how you can update or upgrade your 2.1 system with the EL 4.0. So as we already said, the dimensions changed. So that means the piping needs to be adjusted a little bit. What's also important is the principle is a little bit different in the EL 4.0. So therefore, it is not possible to connect or to combine the oxygen vent lines of the EL 4.0 with the oxygen vent line of the 2.1. So you will have to keep them separate. This is due to high temperatures in the oxygen vent line of the EL 4.0. So we have a new component inside. It's called a recombiner, and it decreases the amount of hydrogen in the oxygen vent line even further. So we've always been below the 2%. 4% is flammable. We were always below the 2%, but now we're going down even more. And therefore, because of this additional component, the recombiner, we have higher temperatures in the oxygen vent line. Then you can still connect the H2 vent line with the H2 purge line of the electrolyzer 2.1. So we have renaming of this port, so to say, because we found out that for some customers, it's a little bit confusing to call it purge line, because purging is usually referred to some nitrogen purging to clean the pipes, etc., which is not really the case in our electrolyzers. So we renamed this port to H2 vent line, but it's compatible with the EL 2.1, so you are still able to connect those two ports, H2 purge and H2 vent. Okay, then generally it is required, or it is in most cases it can be useful to have a water trap in the H2 vent line, but also in the O2 vent line. Of course, two different piping systems and two different water traps to always keep the gases separate. We heard the dangerous situations that can appear if you combine them. So keep them separate. And in the O2 vent line, most probably you will need a water trap. In the H2 purge line, it depends on your setup. If you're able to release the water vapor in the H2 vent line without a water trap, it's totally fine. But yeah, just make sure that you don't have any accumulation. Okay. And yeah, of course, I also have to talk about the dimensions. So as I said, because the unit is a little bit smaller and the position of the ports changed a little bit, you will probably have to do your piping to adapt your piping. On the other hand, you are now able to fit in 7 electrolyzers in one 42 unit cabinet. So that's why we developed it and made it even smaller, because of course also size is an important factor when it is about comparing them to other systems. Yeah. Okay, then let's talk quickly about the new gas connection interfaces. So now we have standard female straight threads. So the advantage is basically you can now use the fittings that you prefer. So depending on your pipes, depending on the especially stainless steel pipes that you're using, you can have you have more possibilities. You can choose several suppliers to provide you the correct fittings. Maintenance becomes a bit easier, and also the interface itself became more robust and impact resistant. Because if for some reason you have a mechanical damage on the interfaces, then you can just replace the adapter without needing to send back the machine and open it and repair it in a very complex way. So that became a lot easier now. Okay, then let's talk quickly about our certification as well. So we are ISO 22734 compliant now. That makes it a lot easier for system integrators to integrate the system in their in the hydrogen side. So we did everything possible to allow integrators fast and easy integration, and to also decrease the deployment efforts, especially in industrial settings. We increased the design rigor and also, of course, the costs and the maintenance demand. And here we can also see that, because of the routing of the oxygen and hydrogen vent lines outside of the enclosure to a safe area, and also like this, when you are routing the vent lines to an outside area and protecting hydrogen oxygen vent lines from mixing up and from ingress, you can apply these ISO 22734 certification very easily. What else you need to do? Enclose systems in an IP rating according to 439, and to protect the system from overpressure by installing and maintaining a P&ID, a pressure release device, according to ISO 41261. Okay, now let's talk about the EMS. The EMS is our software brick that comes with the devices. So also a big advantage of our electrolyzers. So you have a full monitoring and control possibility. You can monitor and control the devices via the Enapter app, which is available in the Apple App Store and also for Android and Play Store. And you can download it for free. You can register yourself. We also have a demo version for those of you who don't have any Enapter products yet. Just feel free to check it out. And then, what can you do there? You can read all relevant sensor data. As I said, you can send commands. You also have an overview of the data of the device. And you will also see warnings or errors. If something pops up, you can also get a notification if you're using the app. So that makes it very easy and useful to use the app. Or also what you can see here in the screenshot, this is from a normal web browser. And yeah, I just choose a device here. And as you can see here on the upper right side, here you see the current hydrogen production. And here you can see all the information regarding the device. And here you can see the last resolved issues. There are some more information, but I don't want to, yeah, want to show you too many things at once. When we go a little bit more in detail, we can see the dashboard here. So here you really have an overview of the sensor data. You can check out values also in the past, and you can see how is the electrolyzer working, what's the current production rate, and the total stack runtime, and so on and so forth. So all kind of sensor data is available here. And yeah, also temperatures, water inlet pressure, H2 stack pressure, and so on and so forth. So everything is possible to monitor here, so that you always have an interview wherever you are. Yeah, that's it. Thank you for your attention. And yeah, if you have questions, feel free to post them in the chat. And then I'm looking forward to answer them. Thank you very much.
Okay, yeah, thank you so much, Philip. That was really, really helpful, I think. And I think it really gives everybody a quick introduction and a good like overview of the EL 4.0. So there were a couple of questions that came up throughout. We can start quite easily with, is there a new lifetime on the EL 4.0?
Yeah, so we are continuously working on improving the lifetime. So we are currently available to give a lifetime of 35,000 hours. So these are the operational hours. So yeah, this is the current number that we can provide, but we are expecting that this number will further increase. So this is just because our test setup is not old enough to run for several years. But yeah, so far our testing units are running perfectly fine, and therefore we can already say that 35,000 hours are okay. But yeah, we're expecting even more. And what should also be considered is that, yeah, end of life in our case doesn't mean that the stack is breaking or the electrolyzer cannot be used anymore. It just means that we reached 80% efficiency. So after 35,000 hours, or probably a lot more, we can still produce 500 normal liters per hour with the electrolyzer, but the power supply, the voltage and current goes up a little bit, and therefore the electrolyzer becomes a little bit less efficient, but it's still working.
Great, that's nice to know. What about the power consumption of the EL 4.0 air-cooled and liquid-cooled variants? Is there any major difference in how much power they consume?
No, it's actually the same. So both units are using 2.4 kilowatt of energy for 500 normal liters per hour. So the power consumption is independent of the device type. So there's no major difference.
Okay. How about this oxygen and water that is going to be discharged into the atmosphere after the process? How does this work?
Okay, so as I said, there are two different lines. Maybe I can show that again quickly. Let me search this slide and share my screen again. 1 second, please. So now I need the laser. Okay, good. So yeah, so here we have the oxygen vent line, which sources in the electrolyte tank. So here we release oxygen together with water vapor. And as you can see in a different line, we have the H2 vent line. Make sure to always keep them separate, of course. And yeah, both of them can contain water. Actually, because here in the oxygen vent line, we're directly connected to the tank. And also here in the H2 vent line, we are extracting the water from the hydrogen so that we are able to reach the 99.9% purity. And yeah, so these are the different vent lines. And yeah, as I said, when you keep them separate, then you can release both of them to the atmosphere, but make sure that you have a distance of at least 3 meters from the two outlets so that they're not able to mix and create an explosive environment.
Perfect. Yeah, and you just use a water trap or something like this to drain the condensation from the oxygen vent, right?
Yeah, exactly. That's what I said before. So a water trap helps you to get rid of the water inside the pipes, and this is necessary because depending on where you are, but if you are in very cold regions, it might be that the water inside the pipes might become ice and then block the lines. And of course, this must be avoided because blocked lines is not good for the electrolyzer. If the gases cannot go to atmosphere, then you will have an overpressure inside the system. It's not that it becomes dangerous, but it will harm the stack and maybe the other components. So yeah, we want to avoid that.
Perfect. There was also a question on the liquid that cools the electrolyte. So I'm guessing this is for the liquid cooling version. What type of liquid is allowed to be put into the liquid cooling loop?
Okay, so for us, it's very important that we have an environmental friendly solution. So you can provide normal water to your cooling circle. Also, because the temperature range that the heat exchanger is working with is in plus degrees. So we have a operation temperature of 5 to 50 degrees in the liquid cooled version. And this is also the temperature range where the cooling agent is usually in. So if you are providing water with 5 degrees, that's more than sufficient. You can even provide warmer water. But if you are, for example, using a fuel cell, which is using another cooling agent, then you can also use, for example, a glycol mixture. Up to 50-50 is totally fine. So 50% glycol and 50% water. If you fear that it might freeze. But if you want to know more about the cooling, then feel free to contact us to, for example, support@enapter.com, and then we can go a little bit more in detail regarding the temperature ranges.
Okay, brilliant. Yeah, and of course, this also means that you actually don't need to worry about having an impact of the water that is put into the liquid cooling loop and into the electrolyzer DI water input. That's just two separate things.
Exactly, those are two separate things. So yeah, we have separate circles here. So the cooling water or cooling agent will not be mixed with the electrolyte. So no worry about that.
Great. Then there was a question on the EMS. How does the EMS actually communicate with the Enapter product?
Okay, so we have Bluetooth and Wi-Fi in our devices. So the data is exchanged via Wi-Fi, but the Bluetooth connection enables you to pair your device or your mobile phone with the Enapter products. So you have basically three different possibilities to communicate with the device. One is with the app, the second one is via the web interface, and the third one is via Modbus TCP/IP. So also if you have a very remote site and you don't have internet access, it's not a problem. You can control your devices also with a PLC, for example, or a SCADA system.
Great. Okay. Next question would be, does the maximum start-stop cycles have any effect on the lifetime of the EL 2.1 or EL 4.0?
Okay, so yes, our devices are designed to work with renewable energies, and of course, in renewable energies, you're always having, maybe not a constant power supply if you're working with photovoltaic PV cells, or if you're having a wind power plant. So the devices are designed to also work with starts and stops. They can also be operating continuously, but we are recommending to not switch them on and off very frequently, because what's happening in the in the AEM stack is an electrochemical process, and to start and stop very frequently, this will harm the stack. So if you're worried about that, then we usually recommend to use like a battery system, so that you can extend the operation times and let the electrolyzer work more continuously.
Great. Then I see a couple of questions on normal ramp-up times and pressurization. Could you explain a bit more about the startup time of the system? Like, what is the considerations we have to take into account to understand how long it goes from cold start to full production operating at its operating pressure?
Okay, so this highly depends on the environmental temperature, so to say, because as I said, it's also here on the slide, the stack prefers a temperature of 55 degrees. So if you are having a startup from very cold temperatures, it might take a little bit longer. From 20 degrees on, so if the electrolyte reaches a temperature of 20 degrees, then the heat up goes a little bit faster, because then the AM stack can already start working and also is heating up a little bit the electrolyte. So generally you need to consider like 15 to let's say around about 30-40 minutes. But as I said, it depends on the temperature.
Right. So
if you have a hot start, for example, then so let's say the electrolyzer has been stopped and then starts again after, I don't know, a few minutes. So it's still hot, electrolyte is still hot. Then the start is very quick. And Max, you were also asking about the pressure. So what's happening is we have a ramp up where the hydrogen in the stack becomes pressurized. We have a maximum output pressure of 35 bar. And so like first we are ramping up, and then we are releasing a little bit of hydrogen via the H2 vent line to get rid of some water vapor, which has been condensating in the pipes. And then we go up to the 35 bar and release the hydrogen to either the attached dryer, we will also talk about that in the next presentation, or to the your tank or compressor or whatever you have attached.
Okay, yeah, very nice. And then there were some questions about DC power supply voltage. So the DC-DC version, what type of input voltage is allowed, was required, and how much current will we draw?
Yeah. Oh, okay. So we have, please correct me if I'm wrong, I think it was 48 volts to 60 volts in the DC version. And we have the same power consumption of 2.4 kilowatts. So that's the values that you need to calculate with. I'm not sure if that answers the question, or what do you think? Goes it a little bit in another direction as well?
Well, I mean, yeah. So the DC power supply will always, have to be, the input voltage has to be around there. And the current, of course, depends on the operation at the time from the system. So.
Yeah, exactly. So yeah, depending on the production rate, it might also differ a bit.
Yeah.
If you produce less, then you need less current.
Yeah. Now there were some questions on the DI water supply as well. So two-part question that we can do: how much DI water is actually consumed, and why do we, if we already have electrolyte inside, how come we keep having to require DI water?
Okay. Yeah, so the electrolyzer consumes around about 400 milliliters per hour. This is necessary, of course, to produce the hydrogen. And the electrolyte is kind of the oil in an engine, so it keeps the system running and allows this electrochemical process that happens in the AAM stack. But yeah, what I think should be said is that the electrolyte itself is not used up. It's just the water. So the electrolyte remains in the tank, is just pumped around, and the electrolyte itself is a 1% KOH solution. So we have potassium solved in water, and the water is used up 400 milliliters per hour, and then of course you need to provide more water to keep the electrolyzer running. If you don't do that, then the electrolyzer will first show you a warning, and then if you still don't provide more water, then it will go into standby.
Nice. Yes, and what type of DI water requirements are there again? Could you repeat this?
Yeah, so for the DI water, you need less than 20 microsiemens per centimeter. The purer your water, the better for the stack. So you can increase the lifetime of your electrolyzer even further if you are using very, very pure water with 2, 3, 4, 5 microsiemens per centimeter. So the lower, the better. And what's very important to say is that you continuously take care of the water quality so that it is not exceeding the 20 microsiemens because that might harm the stack.
Okay. And then I guess there's some general questions on the system safety. So let's imagine that one of the cells in electrolyzer breaks. What would happen? Would the electrolyzer be able to detect this?
Yes. So the thing is, now with the new EL 4.0, we have a hydrogen detection sensor, and this sensor will notify if there is some hydrogen in a place where it should not be. Yeah. So all the connections are of course leak tight, and if there might be some problem, some leakage for whatever reason, then this will be detected via the hydrogen sensor. But we also see that with other sensors. So there are more sensors inside, like pressure sensors and so on, where we will also see if something is going wrong. And then the device will immediately shut down, stop the hydrogen production, and remove the current and voltage from the stack. So nothing can happen here to keep the system always in a safe state.
Right. And of course, there's always the recombiner in the oxygen vent line as well that could detect any sort of increases of hydrogen crossover into the oxygen line. Nice. Yeah, I think we've got a few questions left in the Q&A, but we will collate them, and I think we can answer them at the end again.
Yeah, so let's see, right after this presentation, I will also talk a little bit more about integration tips. So maybe some of the questions will also be answered then. And if not, feel free to still write them to us. And everything that cannot be answered in this session, we will answer that then afterwards, or just write us an email, as I said, to support@enapter.com.